Hi, welcome to part 2. So let's talk more about improper integral. Now there's two types of improper integrals really. One, we have infinity in the domain. That's what we're talking about today. The other part is what happens if we're approaching like an asymptote or something like that. If we include like an asymptote. We're going to talk about that tomorrow. So the first thing we're going to take a look at today is what do we consider an improper integral? Well, this is day 1. So this is basically where we have if we have plus or minus infinity in the domain. Okay? And this is improper because we can't count to infinity. We can't count, we can't equal infinity. You can't equal. It's improper. So that's why we call them kind of improper integrals. So we have ways to kind of make sure we can make these work for us. Now to evaluate improper integrals, we have a couple ways we can do it. One, what if I'm going from like a to infinity? Well, I'm starting at a, I'm going to infinity. So we talked about in part 1, well, the infinity is the problem. I make it just another variable like b. And I take the limit. Since I can't equal infinity, we approach it with the limit. And the same thing down here. What if my infinity is in the bottom? Well, that's in the place of a. So I take a goes to negative infinity of f of x dx. And so what happens is now instead of having a value at infinity, because remember, the value can never equal infinity, we're taking a limit instead. And that's the whole purpose of all of this, is this just to make sure that we're doing these properly. Now, fun one, what happens if we go from negative infinity to positive? Well, we pick a number in the middle. So normally pick 0. So c is just a number. So some arbitrary number that we pick. And we can go from a to c and then from c to b, where we have to set up 2 integrals here. You'll see one like that in your homework and such. Now, example number 1 we did in part 1. So let's go to example number 2. If I want to set this integral up, remember, I can't have this infinity. That's my problem. It's improper. So I'm going to rewrite it by calling that b. And I still want it to go to infinity, so that's where the limits come into play. So we say as b goes to infinity of 1 of e to the negative x dx right there. So as b goes to infinity. Now it's proper, and I can solve this one. Taking the antiderivative, from 1 to b, we get negative e to the negative x. And if I simplify this, b goes to infinity, I'm going to write this as negative 1 over e to the b. The negative tells me to bring it down. And this becomes plus 1 over e to the first. Very simple to do. And now we take the limit, just like we did back in our beginning of this year. We take the limit as b gets larger, the bottom gets humongous, so that just goes to 0, and we're left with 1 over e. So what this is saying is that the function, that the integral converges to 1 over e right there. In other words, it has a finite area. I can, even though it goes without, even though the function length goes without bound, the area converges to a single number. And we can do it for 3. Let's take a look here. For 3, we're down here below, so we'll call it a. So again, I'm going to rewrite my integral as a to 0 of e to the x over 4. Now be careful, take the limit, because I still want to go to infinity, so I still have to take that limit right there. And I forgot my dx. And now when I integrate it, because this is now proper, now like I say, you can solve these without limits. Remember we talked about this example in part 1. You can solve it without limits, but it's just improper. We don't want to. It's just a bad way to look at it. I can take the natural log of infinity in my mind and say it's infinity. We know it's going to approach infinity, but we just say it's improper because we can't really have the natural log of infinity equal to infinity because a value cannot equal infinity because infinity does not exist, only in your minds. So because of that, we say it's improper to write it that way. Even though we will get the same answer, it's improper to do it that way. We want to make sure we're doing it the correct, proper way. So when we take the integral here, I'm going to get e that just becomes e to the 0. Whoops, sorry, forgot from a to 0, e to the 0. Got to take the antiderivative. This becomes 4e to the x over 4. There we go. Sorry, take the antiderivative first. And now I can apply the FTC. X goes to negative infinity, and this is going to become, plug it in, 4e to the 0 minus 4e to the a over 4. Now, I know what this becomes right here, so I'm going to simplify this just a little bit. The limit as x goes to negative infinity, watch what I'm going to do here. I'm going to plug them in. I'm going to get 4 minus 4e to the a over 4. Yeah, I didn't have to do that, I suppose. Now, watch what happens. When I plug it in, this becomes 4. This stays 4. But I get minus. Now, look what happens. If I plug in negative infinity here, this becomes 4 over e to the infinity, basically. I have to bring it down because of negative power. That's 0. So I'm left with 4. So this converges to just 4 right there. Alright. Now the last example, we can revolve this around an axis. Let's take our function e to the negative x. We're going to revolve it about the x-axis. Now the thing they tell me is that it's going to be around the first quadrant. That tells me the domain from 0 to infinity. So if I kind of sketch this out, I know what this graph looks like. From 0 all the way to infinity. You can do like this off to the side there, but don't do that. Don't make a hash mark and make that. That's bad. And I'm going to find this area as I revolve it about the x-axis. And we're going to use our disk. It doesn't take long to set up your disk. Look at this. E to the negative x. Find the volume of my disk. It's pi times e to the negative 2x, I got to square it, dx. And I'm going to integrate that from 0 to infinity. It's improper because of the infinity, so I'm going to rewrite this. Take the pi to the outside. I'm going to write this as the limit as b goes to infinity. Oh, by the way, why did I choose a down here and not b? I could use b. It's fine. But like my normal domain always goes from a to b. A's on bottom, so I choose a. I choose b here from a to b. B's on top. So that's just more tradition. When I integrate this one, now we can go from 0 to b, e to the negative 2x, dx. And I can integrate this. Pi, keep it on the outside. B goes to infinity of negative 1/2 e to the negative 2x from 0 to b. And there's our antiderivative. Solving it now, pi times, this becomes the limit as b goes to infinity. Plug everything, do your FTC, negative 1 over, be careful, I plug this in, 2 over e to the 2b. Or not 2b, right? Bring it down. I brought it down because of the negative exponent. And if I minus, it becomes a plus because of the double negative, 1 over 2e to the 0. So what happens, if I plug in b here, if I plug b in, that gets really big real fast. The bottom shoots off to infinity. That just becomes 0. Plus this, that just becomes 1 over 2, and I get pi over 2, and there's your volume. So the volume here converges to pi over 2. Alright, so we have some examples here. Take a look at these. Go back and try some more if you like. Okay, and I'll see you guys later. Bye-bye.